Hello, I'm JW. Today we're going to have a look at the wiring regulations. This is the 18th edition. I'm going to have a particular look at electric vehicle charging points and the sort of things you need to do when installing such things. Now, looking at the 18th edition, that's effective from January 19. This video has actually been made a few weeks before that, but it's only a few weeks away, so might as well look at the latest edition. And most of the regulations, of course, do apply anyhow, but there is a specific section in there which is specifically for electric vehicle charging outlets. So the section in question is 722, electric vehicle charging installations, and although this is a relatively short section, it's actually only 3 pages in length, important to remember that this is an additional part of information for electric vehicle charging installations. All the rest of the regulations about cable sizing and protective devices and all the rest of the stuff still applies. So in fact it's no real difference there to installing any other circuit. It's just that these things here are of course applicable to this particular situation only. So as we've got here, the requirements of this section apply to circuits intended to supply electric vehicles for charging purposes, and it does not apply to inductive charging, which is where you wouldn't have any direct electrical connection. It's basically just something that drives over a pad in the floor or whatever, and doesn't apply to mobility scooters and similar with 10 amps or less. That's your requirements. You could of course those just plug into a normal household outlet, just as they always have. So it's purely for specific outlets for electric vehicle charging. And if we look down the bottom here, it says that a dedicated final circuit shall be provided for the connection to electric vehicles. It shall be considered that in normal use, each single charging point is used at its rated current, and where the circuit supplies more than one charging point, no diversity shall be allowed. Now this is important because if you're going to install, say, a 32 amp circuit for a charging unit, which is probably the most common one for domestic installations, then when the vehicle is plugged in, it's going to pretty much use all of the current that's available, which is going to be in the 32 amps range. And whilst the vehicle's charging, of course, it's going to use that current all the time at the full rate. So again, no diversity is permitted. And again, it's not something that's like a cooker or something where, although it's got a 32 amp circuit, the current drawn is usually considerably less. It's definitely the case that when it's plugged in, it's using the power, and that's all there is to it. So in that regard, it's similar more really to things like an electric shower, which of course when it's turned on, it's using the full load current 100% of the time. Now diversity in terms of a domestic installation isn't particularly going to be relevant because most people are going to have one electric charging point, but certainly in places like, say, a car park or something where you may have a whole row of the things, important to realise that if it's 32 amps per point and you've got 10 of them, then that's going to be 320 amps of possible demand there, and of course the circuits and equipment needs to be designed to deal with that. And also, unlike things like electric showers, which are typically going to use for sort of 5-10 minutes, a car charging unit could be in use for many hours continuously. So if it's parked overnight or something, it could say sort of 8 to 10 hour charging period, and through that 8 to 10 hours it's going to be using the full 30 amps or whatever you've actually provided there. Now, say a 32 amp circuit is the most common for a domestic installation, although you can put in, say, 16s, and other ratings, of course, are available. For domestic, it's not going to normally be above 32, mainly because the supply to the building is obviously limited to a fairly small value. And bearing in mind, whatever you're adding here is going to be in addition to whatever loads the property already has. So again, it's obviously 32 is generally around the maximum sort of level that you're going to be installing. Now there's two primary things to consider when installing an electric vehicle charging point, and the first of which is the type of system earthing which you've got. Now of course this is going to be dependent on what you've actually got available at the property, and it's going to be one of those 3 things. It's either going to be a TT arrangement, a TNS arrangement, or a TNCS, and we have covered these in another video about the various different types. And there are some very specific requirements here, particularly in regards to a TNCS or a PME, as it's described here, type of system, in that if you've got one of those, you can't actually use the PME earthing facility as the means of earthing for the protective conductor of the charging point. Now, a lot of properties have PME or TNCS supplies, and of course this is certainly going to be a problem if you're not actually allowed to use it. Now, if it's a TNS system, which is essentially where you've got the separate conductor coming in, typically on an older sort of lead sheathed cable or whatever, then you can, and of course would, use the earthing point for that. So that's not really a problem there. And if it's a TT system, well, of course you're going to have to be using a TT system once again, which is the separate earth electrode in the ground. And of course the property is likely to already have one of these, and it certainly should do. you could install an additional one if required. Obviously depends on the condition of the existing one. So for TT and TNS, it's pretty much just using the earthing system which is already there. You don't really get a choice in the matter. But certainly for T and CS, then this is where the things are going to be somewhat more problematic. So as we've got here, a PME earthing facility shall not be used as the means of earthing for the protective conductor contact of a charging point located outdoors, or that might reasonably be expected to use to charge a vehicle located outdoors, unless one of the following methods is used. Now, 99% of vehicles are going to be charged when they're outdoors, and in fact most of the charging points are going to be outdoors, so very much it's going to be applicable there. And bearing in mind, even if you stick the thing in somebody's garage, it's fairly likely they're going to just park the car on the drive and plug it in there. So even if there is the presence of, say, a garage or whatever, in reality it's going to be equivalent of considering it to be done outside. Now, for practical installations, the earthing facility for PME will not be used because, as we'll see in a moment, these three things here, this one, and the one next page, are so desperate and unlikely and impossible to comply with that you're not actually going to be using these things. But in theory, if you did manage to comply with one of I, 2 I's or 3 I's, then you could, in theory, use the PME earthing facility. But just have a look at the first one here. So the first one is that the charging point forms part of a three-phase installation that also supplies loads other than for electric vehicle charging, and because of the characteristics of the load of the installation, the maximum voltage between the main earthing terminal of the installation and earth in the event of an open circuit fault in the PEN conductor does not exceed 70 volts. Now, first of all, the vast majority of domestic installations do not have three-phase of installations available, so you can forget that. And even for places that do, basically what this is talking about here is that the three-phase loads need to be perfectly balanced, or at least as much as possible. And this basically means that the voltage on effectively what is the neutral conductor is not going to actually increase above 70 volts in the event of that being disconnected, because bearing in mind on the TNCS, the cable coming to the building is just the line, and then the earth and neutral are a single conductor. So in the event of that being broken, your neutral is basically no longer connected, and it's going to obviously rise to whatever voltage there is, depending on loads within the installation. So even with a three-phase installation, which say you're never going to have in a domestic, it basically means that it's going to have to be a set of decently balanced loads, so things like electric motors or other three-phase loadings, so that and it's always going to be at that kind of stage. So unless you've got a three-phase installation with only three-phase loads connected, this is never going to apply. And even if it did, there's also other issues where the voltage could, of course, increase there, say a phase dropped out or something like that. So that is never going to happen. The second one here, which is the main earthing terminal of the installation, is connected to an installation earth electrode by a protective conductor. So basically putting in an extra earth electrode or earth rod and connecting it to the supplier's provided earthing terminal. This generally can't be used, and we'll have a look at this in a moment, but the main criteria here is that in the event of the cable being an open circuit fault, the conductor does not exceed 70 volts RMS between the conductor and the actual ground, and we'll look at the calculation later, and basically that's pretty much impossible. And the third one, which in theory could use, is that protection against electric shock is provided by a device which disconnects the charging point from the live conductor of the supply and from the protective earth in accordance with this regulation, connects within 5 or disconnects within 5 seconds, and it's in the event the voltage between the circuit protective conductor and earth exceeds this 70 volts RMS again. And it should not operate if it exceeds 70 volts or less than 4 seconds. The device shall provide isolation, and closing or resetting is by manual means only. Equivalent functionality could be included within the charging equipment. So this is a device which monitors the actual voltage between the protective conductor, which is the one that's provided by the supplier, and the actual real earth, as in it's going to have its own sort of electrode or connection to that. If the voltage exceeds its 70 volts, it's going to disconnect both the line, the neutral, and, most importantly, the protective conductor as well. And this is to prevent dangerous voltages appearing there. So again, if that combined conductor was broken, any voltage that shows up on the protective conductor is going to be disconnected, and it won't present a hazard to those persons using the equipment. Now, at the time of making this video, which is in November 2018, these devices don't actually exist. And although it states here that it could be included within the charging equipment, certainly at the moment that's not something which is actually an item that exists. Of course, it may do in the future. This is effectively similar to the old voltage operated earth leakage circuit breakers which went out in the early 1980s. The only difference here is that this will disconnect the protective conductor as well as the other two, meaning the whole thing is totally disconnected. So if you can get one of these devices and install it with an earth electrode and all the other gubbins it needs, then of course that's an option you could use. But at the moment it's not even something that's necessarily available, and even if it was, it's not certainly a trivial thing just to stick in there and make work. Now in reality what you're going to do if it is a TNCS system is to not use the PME earthing facility and instead just actually install an earth electrode specifically for the car charging facility, connect that and use that as the earth connection for the charging equipment, and most importantly do not connect your earth electrode to the existing earthing facility for the building. So you're basically ignoring the supplier provided earth connection, not using that at all or connecting to it in any way, but you're going to put in your own earth electrode in the ground, do the recommended tests and things on that, and again that's all in the other part of the regulations, and then that and that only becomes the earth connection for the charging equipment. And this one here about putting in the electrode and connecting it to the earthing facility is a big fail because as it says here, the voltage in the event of a fault between the earth electrode and the supplier's conductor must not exceed 70 volts. So let's just have a look at the calculation it says here in 722, see why that's realistically never going to happen. Now if you were going to use that highly implausible option, this is the calculation here, and this is actually an Annex 722, that's A72.3 there, and it says here, for the purposes of condition 2 of regulation there, which we just looked at, the sum of the resistance of the earth electrode and the protective conductor connecting it to the main earthing terminal must meet the following condition, and we've got two here, which is basically a single phase and a three-phase installation. They both sort of add up to pretty much the same thing. We'll look at the single phase one here. So we've got RAEV is smaller than or equal to this formula here, which is basically 70 times the voltage. This is the installation current, and then it's multiplied by, again, the voltage minus 70, so it's one divided by the other. Now we can see the definitions here. So again, the I inst is the maximum demand current of the installation, including that of the electric vehicle charging load and any other loads. So basically it's the total load of whatever the building or installation is. UO is the normal AC RMS line voltage to earth, so it's going to be your 230 in most cases. And RA, of course, is the sum of the resistances of the electrode and the protective conductor. Now, the protective conductor is going to be of tiny resistance anyhow, because generally it's going to be a fairly substantial piece of copper. So it's primarily going to be the resistance of the earth electrode, and that's essentially the absolute maximum that it can be. And in ideal circumstances, of course, it would be less. So let's just write that out and put some sample values in and see what kind of fail we can actually get. So the formula in question then is basically 70, and then it's UO, so we use the 230 for that. So those two are multiplied together, and then that's divided by UO minus 70, so that's basically going to be 230 minus the 70. And then the value here is the actual current of the installation. Now we'll just put that in as that I inst for the moment, and that's basically multiplied by that as well. And whatever the result of this is the maximum for the actual resistance of the electrode and the conductor. Now to make that a bit easier, just rewrite this with the actual things obviously calculated there. So the value at the top is 70 times 230, which is 16100. And then at the bottom, the 230 minus 70. Of course, that's going to be 160. And then the I inst, which is the load of the installation. And we can put in a sensible value here. Now, bearing in mind, this has to include the load of the particular charging vehicle. So that's going to be in the region of sort of 32 amps or so. And then we have to add on, of course, any other loads within the property itself. So, of course, that's generally whatever happened to be in there. So let's go for a fairly low value to start with. So let's say we had the 32 amps for the actual thing there. And let's have a really implausible, say, 8 amps for the installation itself. So, of course, that will be 32 plus 8. That will give us a total load of around 40 amps there. So that would be 40 times 160 in the bottom. And essentially what this divided by that is going to be the maximum resistance that we can actually have. So 40 times 160 is 6400, and of course it's 16100 on the top. So 16100 divided by 6400, and the result for our maximum impedance there gives us a result of 2.5 ohms. Now, if you're going to put an electrode in the ground, good luck getting anywhere near that, because in most cases that's actually going to be next to impossible. Bearing in mind for the rest of the regulations, typical value for an electrode is in the region of 200 ohms or less, and in some cases maybe sort of in the region of 100 or so. And if you're actually going to put these things in practicality, it's generally relatively easy to get in the region of sort of 50 ohms or so. Not really a problem. But getting down to 2.5, well, that's next to impossible. You literally have to be sort of digging up the entire garden and putting in a huge grid or mesh underground, and possibly encasing it in concrete as well, and who knows what other bother. So shoving in a rod and connecting it to the existing TNCS earth is not going to be realistic, because you simply won't be able to get it down to this kind of level. And bearing in mind that was only with a total load for the whole installation and the vehicle of 40 amps, which gave us that sort of rather unlikely 8 amp load for the rest of the property. So it's just turning on a washing machine or tumble dryer, and you're going to be above the 8 amps there. Now let's just try that again. Let's use a different value this time. So we just have what we had on the previous page, which is the 16100 divided by the load times 160. Let's say the load was only the electric vehicle charging, and that would be simply in the region of say 30 amps to be a bit more generous. That gives us 16100 divided by 4800. So in this case, assuming we only go for the 30 amps of the actual vehicle, our maximum resistance for the electrode is 3.4 ohms. Again, a highly implausible and unlikely figure. And in fact, to get anywhere near a sort of credible value, which has been the sort of 10s or 30s of ohms or so, we would actually have to go for not a value of 30, we would have to have a full load current installation of only 3 amps. And of course that's not going to happen anywhere, because clearly the vehicle itself is more than that. And of course if it was 3 amps there, that would give us a total resistance of 34 ohms, which at least is reasonably realistic. Certainly possible to actually get somewhere near that. But again, you're not going to have an amperage of 3 amps full load for the entire installation, including the vehicle. Charge up your Tesla model, whatever else, with 3 amp load. It's going to take 10 years to actually do so. So, although in theory you can use that option 2 there, in reality it's going to be impossible, because you won't be able to get the electrode resistance low enough. Simply the fact that getting things in this sort of single-digit ohms is next to impossible. So in summary then, depending what earth system you have, these are your options. So if it's a TT installation, then basically you're going to be using it as what you've got there, no particular change there. For TNS, typically older sort of lead-covered cables coming in the older properties, then as again you can use TNS just as you would before. You could, of course, not use TNS. You could, of course, just put an electrode in and use it as a TT installation. This may be worth considering, because a lot of the older ones are being upgraded or changed, and when they're upgraded or changed, they inevitably end up as TNCS. So, although you can use the TNS earth connection, it may be worth doing it as a TT anyway, just to avoid any problems in the future. And if you've got a TNCS installation, which again is pretty much the default choice for any new or newish property, your only realistic option is to use it as a TT installation, because as they saw there, those 3 things can't be used in reality. They're completely impractical, and certainly not something you're going to be using in any real situation. And by putting it to TT, what we mean is a separate electrode for the installation only. That would be the EV installation. And it is not connected to the TNCS earth. So an entirely separate installation, an earth rod specifically for the earthing for the electric vehicle charging equipment, and you're definitely not going to connect it to the TNCS earth in any way, because again that just comes back to that same problem we had before, where you have to get it in the ridiculously low 2 or 3 ohms area. And if you do it as a TT, of course it would have an RCD on there, but it's just then the same as any other TT installation. So you're looking for values of in the region of sort of 200 ohms or less, and in many practical terms sort of say 100 ohms or less, depending on which set of books and guidance you actually read. So standard electrode in the ground there. In most cases one is going to be sufficient, or if not you can also put two or more in, and as long as it's in the region of say 100 ohms or so, absolutely fine. And the crucial point is not to connect it to the existing supplies earth at all. You're then treating the installation of the charging equipment as completely separate and unrelated to whatever's coming into the building in terms of the earth provision. Now let's have a quick look at some of the other things on the section 722. You can use electrical separation if you really wanted to, but as it says here, this is limited to the supply of one electric vehicle supplied from one unearthed source, and it's supplied through a fixed isolating transformer complying with this standard. So you could use an isolating transformer, but providing it's only providing one electric vehicle charging point. The problem here is that a isolated transformer capable of dealing with 32 amps on a continuous basis is going to be a very large and heavy piece of equipment. It's all going to be quite expensive, and quite frankly nobody is going to go for that option, but nevertheless it's an option that's there if you really wanted to use it. Now a lot of the rest of this here, which is things like if it's installed outdoors, it obviously should have a protection of the IPX4 and so on, and obviously should have things like foreign bodies getting there. All of this is fairly common sense anyhow, and in pretty much every case you're going to be purchasing a pre-assembled unit for the actual charging equipment. So all of this of course will be taken into account anyhow. These things are obviously designed for the purpose, provided they obviously meet these standards here, which in 99% of the cases they of course will. This isn't something to get particularly too concerned about, because say in terms of the actual installation, typically it's going to be something like a 32 amp circuit from your existing consumer unit or whatever, cabling going outside to the particular location, and then the charging equipment is basically a self-contained device which you're just going to wire in, fix on the wall in the appropriate location. Now all of these require an RCD, and the particular type of RCD we require is at least type A, and operating current not exceeding 30 milliamps, and for each one containing a socket outlet or vehicle connector. Protective measures against DC fault current shall be taken, except where provided by the EV charging equipment, and this can either be an RCD type B, an RCD type A, and appropriate equipment that provides disconnection of the supply in the case of DC fault current above 6 milliamps. Now of course you can buy RCDs of these particular types, and in fact one specifically designed for electrical vehicle charging points. However, in reality the RCD is generally going to be incorporated into the charging device, so the circuit from your supply, it's going to say things like armoured cable or whatever, it doesn't actually need an RCD, and then this is going to be built into the charging equipment. In the unusual case where the charging equipment does not have an RCD in it, then you would of course need to provide one of these generally inside the property for that particular circuit, but in most cases it's going to be part of the charging equipment, so again not something you need to desperately do as a separate item. And then over the page, the RCD shall comply with one of these following standards, which are basically the standards for RCD, so no real surprises there, and it shall disconnect all live conductors, so again that's pretty much standard there, just be a two-pole RCD with line and neutral in the event of a single phase supply. So all pretty much standard stuff there, but just be aware of the particular type of RCD that is required. It's not just the normal 30 milliamp type you would put in say a house for example. Devices protection against overcurrent. Each charging point shall be supplied individually by a final circuit protected by an overcurrent protective device complying with one of the choices here. That's going to be your normal, say, circuit breaker in most cases, the 60898, and say more typically going to be a 32 amp circuit there. And notably it needs to be an individual circuit, so if you're going to have say two of them installed, then they each need to have their own circuit and their own protective device. And again, generally people are going to have one certainly at their house there. And I know here that the charging equipment may have multiple charging points, so if you have a device that say had two connection pieces on it, that can be supplied from one circuit, but if you're putting in two separate charging outlets, then those need two separate circuits for those. Now in terms of the actual socket outlets and connectors, there's a whole load here about the various types of charging points you can have, and the types of vehicle connectors and the types of socket outlets and so on you can have. Generally you can either get these with the lead pre-attached, which is basically what we've got down here, and then the wire sort of permanently attached, and it's got a big plug on the end that goes into the car, and some other types just have a socket on there, And then of course the lead is actually with the vehicle itself, so you could take the lead out and plug it into the car, and the socket outlet on the charging point as well. But again, you're going to be buying the sort of pre-assembled unit of the appropriate type for the vehicle in question. So again, as long as it complies with one of these items here, not actually a problem. And of course there are different types of vehicles and different types of connector that they have. And again, the final parts here, a lot of this does refer to the actual charging equipment, such as it sort of prevents the plugging and unplugging the plug unless it's switched off from the supply and so on. But again, all of this is pretty much going to be built into the charging point equipment. So as long as you're buying something that's made to a decent standard and is intended for the purpose, again, this is not going to be a particular problem. So that's electric vehicle charging points. And in terms of the actual circuit to the charging equipment, it's pretty much the same as any other circuit. Types of cable and size and protective device and everything else applies just as it would to anything else. And the actual charging equipment, generally going to be buying that as a pre-assembled unit with the appropriate RCD and whatever already inside, and of course the appropriate connector or socket for the vehicle that's going to be charged there. So all of that is pretty much just standard stuff. The important points to remember are the type of earthing that you're going to be using. And in most cases, this is going to mean you're going to be putting in a separate earth electrode and using that as, say, a TT installation just for the charging equipment, and most importantly, not connecting that electrode to the earth supply that's provided by the electricity supplier. So in the case of a TNCS installation, it's going to be impossible to use one of those three options which were given in the examples there in the regulations. So a TNCS, it's always going to be putting in an earth electrode, using that earth electrode only and not connecting to the TNC earth in any way. If it's a TNS system, in theory you could use that as the earth, but in reality it's probably a good idea to put in the electrode anyhow and not use it, because a lot of the older ones are being upgraded with cables being replaced and the like, and of course when that happens it turns into a TNCS anyway, so of course there's the same old problem. And of course if you've got a TT installation anyway, well obviously that's all you can use. So earthing is quite important, but realistically it's going to come down to putting in the earth rod and using that only, regardless of what type of supply you have. And the only other thing there is really the RCD type, so it does need to be this specific one which reacts to DC fault currents as well as AC. But again, in most cases that's going to be built into the charging point itself, so again it's just going to come along with that. If in the case it doesn't, of course, you will need to provide an RCD of the appropriate type for the actual circuit that you are installing. But say most of them seem to come with a particular RCD in the charging equipment anyhow. So that's pretty much it for this time. Until next time, thanks for watching.